Okay, so welcome everyone for today's quantum space-time seminar. Today we are very happy to have Tom Hartman from Cornell, and he's going to tell us about average null energy and renormalization group. Over to you, Tom.
All right. Thanks a lot for having me. It's good to see everyone. So I'm going to tell you about some work that's been in two papers so far with Greg Mathis, who was a postdoc here and is now just moved to EPFL. And let me say from the beginning that I'm happy to make this a discussion. So please just interrupt me with questions as we go. And I have my iPad connected so I can write equations and everything, and we can talk things out. Okay, so the basic idea, the basic thing that we're going to be doing here is we're going to be talking about the average null energy operator. So the average null energy operator is this thing. Actually, can you see my cursor my cursor on here? You can.
Yes.
Okay, good. Yeah. I'm never sure with Zoom. Okay, so the average null energy operator, we take the null components of the stress tensor and we integrate those over a null ray. So in two dimensions, this is essentially, under some assumptions, this is the null momentum generator. But in higher dimensions, it's localized in the transverse direction. So this is not a conserved charge or anything, but it's an interesting operator. And this operator has been showing up in various places. It's related to quantum information through calculations of the modular Hamiltonian. It's important for correlators in the Reg A limit. So it's related to things like the chaos bound and sign constraints on the couplings. It obeys a positivity condition, which is called the ANEC, which we'll talk about, but this is responsible for various inequalities in quantum field theory and conformal field theory. And what we're going to do in this talk is to make another connection to a topic in quantum field theory, which is the c-theorems for renormalization group flows that govern what quantum field theories can flow to each other in 2 and 4 dimensions. So the goal of the work is to show that the ANEC implies the c-theorems in 2 and 4 dimensions, and hopefully get some new insight into how those c-theorems work. Here's an outline. So I'm going to start with an introduction describing some of the ingredients here. So the c-theorems, the average null energy operator, and the average null energy condition. Then I'll talk about various sort of technical things to walk you through the calculation involving these correlation functions of light ray operators and contributions from the conformal anomaly. The goal of this talk, the goal of this part of essentially the main part of the talk, the goal will be to derive the a-theorem from the ANEC. So the a-theorem is the 4-dimensional c-theorem. The 2-dimensional case is similar, but we're going to focus here on the a-theorem. And then if there's time, I'll have some comments at the end on connection to Lorentzian inversion. So let me start with the background, the introduction. So a quantum field theory, as opposed to a conformal field theory, a quantum field theory can be thought of as a renormalization group flow between 2 conformal fixed points. At least a quantum field theory that on its own is completely well defined is an RG flow, where we have a conformal field theory, we have a conformal fixed point CFT UV at high energies and CFT IR at low energies. Then the renormalization group connects the different conformal field theories together, and those are sort of the building blocks for the space of quantum field theories. It's been a long-standing question how to understand what quantum field theories can flow to each other. There are lots of different ways of studying this, but this subject is guided by the idea of c-theorems, which are theorems that tell you that constrain these flows. So a c function, and so a c function is if it exists, is a function that is defined intrinsically at the conformal fixed point. So it's a universal function that depends only on the CFT data at the fixed point. that you can think of as counting degrees of freedom. And furthermore, it decreases under RG flow. So it's something intrinsic to the fixed point that decreases under RG. If a C function exists, then in a given dimension, then the renormalization group is irreversible. So this was the notion introduced by Zamolodchikov in 1986. So also a word about terminology. So there's the c-theorem in 2 dimensions, there's the f-theorem in 3 dimensions, there's the a-theorem in 4 dimensions. These are all examples of the capital C c-theorems. So the terminology is a bit of a mess because nobody knew in advance which functions would be the C functions. So they gave them different names, and now we have c-theorem in 2D, F and A. But these are all C-theorems, capital C C-theorems. In 2 dimensions, the Zamolodchikov C-theorem is a statement about the 2-dimensional central charge, the Virasoro central charge at the fixed point. So that's something that's completely specified at the CFT and decreases under RG flow. The way Zamolodchikov's argument works is he studies the stress. So what I've listed here on this slide are the way that these arguments are derived, the way that these inequalities are derived. So in 2 dimensions, the derivation starts with the stress tensor 2-point function. We apply conservation, reflection positivity, and combine various components of this stress tensor 2-point function into something that's positive and a derivative that's positive, and therefore some monotonic quantity along the flow. So that's how the original Zamolodchikov argument worked. And there's been attempts and progress on extending that to higher dimensions over the years. So that was already many years ago in 1986. Going in dimensional order, we also have now a C-theorem in 3 dimensions. F is the free energy on a 3-sphere. So F is the path integral on a 3-sphere. And in this case, the arguments are very different from the Zamolodchikov argument. The physical intuition for the result is similar. It's supposed to be a count of degrees of freedom, but the arguments are very different. This relies on quantum information, strong subadditivity of the quantum entropy, and various clever applications of entropy inequalities by Cassini and Huerta. In 4 dimensions, well, the even dimensions are on a similar footing, but in 4 dimensions, so in 4 dimensions, the thing that decreases is again related to the conformal anomaly. So A is one of the anomaly coefficients in the trace of the stress tensor, as we'll talk about. But the reason it took so long, despite a lot of attempts, the reason it took so long to get from 2 dimensions to 4 dimensions is that the method that you need to prove positivity is a lot more intricate. And what Komorgatsky and Schwimmer did is they coupled the theory to a background dilaton, and then they studied the scattering amplitudes of the background dilaton. You can roughly think of this as a study of the stress tensor trace 4-point function. So theta in my notation will always be the stress tensor trace. And the Komorgatsky-Schwimmer argument for the A-theorem is, roughly speaking, an argument about the trace 4-point function. I say roughly speaking because it also involves some contributions of the lower point functions. So it's really the 2, 3, and 4-point functions all combined in some intricate way. What about higher dimensions?
Hi, Tom.
Yes.
Sorry, Tom. Just to ask you, so it's combination of 2, 3, and 4-point functions, but all of the trace of the energy momentum tensor. Is that right?
That's correct.
Okay. Thank you.
Hi, Tom. Can I ask a question?
Sure. Yeah.
So in all these cases, if the IR theory is some gap theory, a massive theory, I presume that is interpreted as C equal to 0.
Correct.
Okay.
Yes.
Thanks.
Hi.
Hi.
For the A-theorem, you mentioned that you are coupling dilaton to your theory. The background, the dilaton is in the background. Is there any? I couldn't follow why coupling to the dilaton is same as talking about the stress of trace of the stress energy tensor?
Well, the background dilaton is essentially a source. It's the trace mode of the metric. And so if you vary with respect to that, then you're calculating trace correlation.
Okay. Got it.
Dilaton is like the source.
Got it.
Yeah. So the status now is that we have these c-theorems in 2 and 3 and 4 dimensions. But in higher than 4 dimensions, it's unknown whether there's a c-theorem. There's progress in 6 dimensions. There's a supersymmetric version that works. There's a perturbative one that works, but we don't have a general c-theorem in more than 4 dimensions. And to me, this is very mysterious. So the words we say usually when we introduce c-theorems are that they count degrees of freedom. And when you do RG flow, you integrate out degrees of freedom. So it seems like it makes a lot of sense. It's very intuitive that under RG flow, you integrate stuff out, the degrees of freedom should go down. But the actual c-theorems are not really related to these words, or just barely related to these words. I mean, the quantities that are decreasing, it's not at all clear why those are measuring degrees of freedom. To me, this is still something that requires more explanation, and I think there's still a lot of interesting physics hiding in these c-theorems. They're still fascinating and mysterious despite all this progress. We don't know why they work, in the sense that there's some formal derivations, but I don't think we really know why these are the quantities that measure degrees of freedom, at least in more than 2 dimensions. The two-dimensional case is a little more clear, because the central charge controls the free energy. And we don't know how generally it works. We don't know how to extend them to higher dimensions. If we really understood how to count degrees of freedom, then we should be able to do it in any number of dimensions, right? So we don't have the universal explanation. If you think that you do know why these quantities measure degrees of freedom, then you should also be able to tell me why in 4 dimensions a fermion has 11 times the number of degrees of freedom of the scalar. So this is the proportionality of the A anomaly in 4 dimensions. So what on earth is going on there? That's just one thing that I think we should be able to answer. Is there a question?
Sorry, Tom, not a question, but just a remedial kind of question, which is, I know very little about this subject, but let's say, just to take your thought forward, I were to do something very simplistic, like look at the temperature, look at the CFT on a sphere at some finite temperature. You might think the prefactor in the entropy should be a count of degrees of freedom. And that very simple-minded way of thinking about things doesn't work in general, I guess. Otherwise, you'd have told us that.
It doesn't work. No, there are counterexamples. There are counterexamples to that one.
Gosh, I see.
Okay. In 3 dimensions, there's a counterexample it's something involving the Ising model, the ON model, where I think, can't remember exactly, you gap out one of the scalars maybe.
I see. Wow. Okay, thanks.
Okay, so the other background that I want to talk about is this operator, the average null energy operator. So I'm using null coordinates u and v. So u and v are the 2 null directions in Minkowski space, and then we have a transverse direction x vector. And the null energy operator is the integral of the null energy over the null ray. All of my null energy operators will be inserted through the origin. So I'm setting v equals 0 and x vector equals 0 in this operator. This is an example of a light ray operator. These light ray operators have played an increasingly important role in various things. They are the basis of the Hoffman-Elisena conformal collider setup and the conformal collider bounds that they derived. They are an infrared safe observable for particle physics, which is complementary to the S matrix. I have a an example here to prove it. So this is a recent paper by the CMS collaboration. And what they do in this paper is to use use the null energy operator. They use the null energy operator to determine alpha strong. So actually, these null energy correlators are now the best way that we have of determining alpha strong from experimental data.
Wow.
They're related to causality and ADS CFT. That's also connected to these conformal collider bounds. And light ray operators are sort of the leading term in the Lorentzian inversion formula of Karen-Huot and conformal field theory. One of the things, so there are many, this is just one example of a light ray operator. You can find many other light ray operators, and they're interesting for various reasons. But one of the reasons this particular one is so interesting is because it's positive. So the ANEC, or average null energy condition, states that it's a positive operator. In other words, the expectation value of this operator is non-negative in any state. The history of this inequality is that it originally came from the relativity community. So in GR, you need to assume something about positive energy in order to prove all the famous theorems about things like causality, no traversable wormholes, singularity theorems, etc. And well, we know that the stress energy, the local stress energy itself, cannot be bounded from below in quantum field theory. So you have to do you have to talk about some kind of non-local operator. And it was understood by the relativists in the 80s or early 90s that the average null energy seemed to be sort of the least amount of integrating you could do and still get something that looked like it appeared to be a positive operator in various examples. And then people derived the average null energy condition in free theories and 2D CFTs in the early 90s. More recently, there are two different derivations in interacting quantum field theory in any number of dimensions. The first one by Faulkner and collaborators is using quantum information. So the way that works is they look at the modular Hamiltonian for a Rindler space. Then they deform the Rindler space by some amount and apply some quantum info inequalities to that deformation. And it turns out that an ANEC operator shows up as the leading term. The other derivation was together with Sanipan Kundu and Amir Tajini, we showed that the ANEC follows from studying correlation functions. Essentially, it controls certain limit of the 4-point correlation function, and then analyticity or causality of that 4-point function gives you positivity of the operator.
Tom, one question.
Yeah.
Stupid. Given that this U integral is to be done from -infinity to infinity, in what sense is it an operator acting on a state that is defined on some space like Cauchy slice?
It is an operator acting on a state on a, but there's no problem with the fact that it goes to past infinity. It could be infinite if your state is not sufficiently localized. The null energy, the average null energy, could be infinite, but it's just an ordinary operator. For example, the null momentum operator is also integrated like that, and that's a perfectly good operator acting on the Hilbert space.
Okay.
We do have to be careful about that point at infinity. So a lot of the discussion in the last few years of multiple light ray operators and whether they commute and things like that has been, a lot of it is about the subtlety of how to deal with that point at infinity and whether it can contribute. But for my purposes, we're only going to insert one of these operators, and then you don't have to worry about that.
Okay.
So now I'm going to move to the new results. First, here they are. So the new results, first of all, the ANEC implies the c-theorem in 2 dimensions and the a-theorem in 4 dimensions. So we're going to find a way of writing the c-theorems as the ANEC. In the process, we're going to derive some sum rules for the change in the C anomaly and the change in the A anomaly. So here I'm just going to flash them up. We're going to derive these next. So let me just tell you what the ingredients are. So in delta C in 2 dimensions, we have an integral of some kernel, this U1 minus U2 squared. There's an integral over Minkowski space of some kernel of a 3-point function. This is a Whiteman function that involves the trace, theta is the trace, and the null energy. Similarly, in 4 dimensions, we have a sum rule for delta A. It's almost the same formula. The only difference is this kernel is a little different. There's now an x1 dot x2 in the transverse directions. Again, the 3-point function. So conceptually, these are relating the, well, I've written them here in terms of the ordinary null energy, but you can also use translation invariance to move the U integrals onto the null energy term here, and then you get some rules that involve the average null energy. So conceptually, what we're deriving here are some rules that relate the effective action, or in this case, the flow of the effective action under RG, to some contributions of light ray operators in the quantum field theory. And that will be our goal.
Sorry, Tom, is the statement that the right-hand side is an expectation value of the null energy, average null energy in a state?
Not quite in this formula, but we'll come back to that later, and we'll have a closely related formula, which is the expectation value, and therefore gives us positivity. Okay. It's not obvious from this formula that I've written.
Okay, thank you.
Are there any other questions?
Sorry, Tom, I have just a very simple question. I haven't understood the statement. So the left-hand side, say in the first line, is the change in central charge under RG flow, I imagine, right?
Correct.
And the right-hand side is an expectation value being computed where? I mean, in a particular CFT along the flow or what? Sorry.
These 3-point functions on the right are 3-point functions in the QFT that's flowing. Okay, so for example, a simple example to keep in mind would be a massive free field, like a massive scalar. And I'll show this example later. A massive scalar. So then it's flowing from a massless scalar in the UV with C equals 1 to a gap theory in the infrared with C equals 0. And this correlation function would be calculated in the massive theory.
Okay, I see. Now I get it. Okay, thank you.
Okay. Are there any other questions? So now I'm going to walk you through the calculation. The goal, as I said before, is to get to this number 4, the A-theorem from the ANEC. We're going to focus on the 4-dimensional case. 2 dimensions is quite similar. In fact, you can do quite a bit more in 2 dimensions because it's easier, but I want to focus on the 4-dimensional case. It's a little more novel. So the object that we're going to study is a retarded 3-point function. And I'll try to tell you why in a minute, but let's just start by defining this object. So this is, you can think of as a response function or a retarded correlation function. And the retarded correlator is defined on this line here. So we're calculating the retarded correlator of the null energy and the null energy trace. This retarded ordering means that you take these nested commutators. So it's a nested commutator, then you sum over, you symmetrize under theta of x1 and theta of x2. That would be sort of the textbook maybe the first thing a textbook will tell you about the retarded ordering is that is this nested commutator, but the nested commutator makes sense only at separated points. It's going to be absolutely crucial to everything I say that we're very careful about the contact terms. And these nested commutators don't make sense at coincident points. So we have to worry about how the contact, but the correlation function does. So this retarded correlator is the well-defined distribution. It does make sense at separated points. There are delta functions that are well-defined, but we'll have to make sense of those contact terms as we go. So now we take this retarded 3-point function and we integrate over the null direction, the u direction, the u3 direction for the null energy, and get the retarded correlator of the average null energy operator. So that's this thing where we have a null energy operator and two traces. All I've done here is expand out the terms and do the integral, but you'll notice that on the right-hand side is now a Whiteman function. So this is a Whiteman function. What's happened is that when you expand out the commutator, there's a lot of terms. There's like however many terms there are, 6 or 12 terms there, and most of them are 0 because the average null energy operator has this nice condition that the average null energy operator annihilates the vacuum. That can be understood. Actually, any positive operator with vanishing expectation value must annihilate the vacuum. This is a very old argument of Jaffe and others. Basically, if it doesn't annihilate the vacuum, then you can form superpositions of the vacuum and whatever you get. When you hit the vacuum, you can form some simple superpositions that violate positivity. So I've used that condition here. I've just expanded out the nested commutator and then dropped the terms where the ANEC is acting on the vacuum on the left or right. So why are we looking at the retarded correlator? Well, the answer is essentially that it works, but we tried various things, and this is the one that worked. But now in hindsight, I can sort of tell you the answer. It's that we're going to take these contact terms and relate them to the conformal anomaly. The contact terms in this correlator will be related to A. And then this other term, the Whiteman function term, will be positive by the ANEC when smeared appropriately. We could have used one of the other ordered correlation functions. All of the ordered correlation functions have these contact terms. And in fact, there are similar sum rules for the time-ordered, starting from the time-ordered correlator. But the advantage of the retarded correlator is that it's easier to smear this function here and make it positive. So if we had started from the time-ordered correlator, it would be, we'd get a similar sum rule, but it would be harder to show that it was positive. So that's why we're using the retarded one.
So sorry, Tom, just to make sure I understand the left-hand side, you take a usual commutator, but by saying it's retarded, you ensure that it's non-zero only if every term to the left is at a later time. Is that correct?
Up to contact terms, that's correct.
Okay, even for the, okay, so even the retarded commutator has these contact terms. Okay,
that's right.
I see.
Yeah.
I see. Okay.
And one other question. Can we interpret this retarded correlator as being related to some wild rescaling of the ANEC operator or ANEC 1-point function?
Yes, you can. So that's it's also the leading term in it's the change in the 1-point function of the null energy under a Weyl rescaling.
Okay,
and
I see. Okay.
The final formula that we'll end up with also has an interpretation in that sense.
Okay, thank you.
Now
sorry to slow you down, but just to understand, since the contact terms are so important, what is the independent definition then of the left-hand side that determines?
I'll get to that in 1 sec.
Okay,
I'll do that. That's right here. Good.
Okay, thank you.
Okay, so contact terms and Lorentzian signature. So I think contact terms usually we talk about in Euclidean signature. In Euclidean position space, contact terms come from consistency conditions applied to the correlator. So in this case, the consistency condition is just the fact that that stress tensor correlators are variations of the effective action with respect to the background metric. That gives conservation of stress energy, and the conservation law at coincident points requires delta functions in the correlator. So in Euclidean position space, those just show up as these delta functions. If we do the Fourier transform to momentum space, then they become terms that are analytic in momenta. So the contact terms are analytic in momenta. Now we can Wick rotate to Lorentzian. If we use the usual Wick rotation, like the one in Peskin and Schroeder, then the Wick rotation of the Euclidean correlation functions on the usual contour will give us the time-ordered correlation functions in Lorentzian. And so there are terms, so we immediately get the contact terms in the time-ordered correlator from those in the Euclidean. So those will give terms that are analytic in momentum in the time-ordered correlator. What about the other?
I have a question.
Yes.
Like these contact terms, in the first line you have x1 equals x2, x1 equals x3, etc. But can't there be any contact terms with x1 just being equal to x2 and not equal to the x3?
Yes, there can. Yes, there can. I'm going to ignore them for now. I have a slide about them later. Yeah.
Okay.
Yeah. Okay, so what about the other Lorentzian correlation functions? So now we have to look at all the different orderings. First of all, Whiteman functions do not have contact terms. Whiteman functions, like this O of k, O of minus k here, the double brackets just means I've deleted the delta function. These Whiteman functions, these have no contact terms for the following reason. If we insert a complete set of states in the middle here, this is something you can do with Whiteman functions, but not with a time-ordered one, say. If we insert a complete set of states here, then it has to be supported only on positive energy states. In other words, on momentum in the forward light cone. That gives you these theta functions, these step functions in the Whiteman correlators. I'm doing the 2-point function here, but there's similar statements about the higher point functions. And it's impossible to have an analytic function with step functions in it. Okay, so there can't be analytic terms in the Whiteman function, so they can't have contact terms. But the time-ordered, anti-time-ordered, retarded, and advanced Lorentzian correlators, those all have contact terms. In fact, they're all analytic continuations of each other that agree in some region of momenta. So there's some choice of momenta where these ordered correlators all agree with each other. And that means that we can relate them to each other by analytic continuation in complex momenta. To give an example of this, let's look at the 2-point function. So it's a trivial commutator identity that the retarded 2-point function, the commutator, is a time-ordered 2-point function plus some extra Whiteman stuff, in this case, just a 2-point function. And now we can take this trivial commutator identity and use the fact that the Whiteman function has no contact terms to say, so now if we look at the contact terms, the time-ordered and the retarded correlator have to have the same contact terms. This argument extends to endpoint functions. And in fact, the endpoint functions, all the different orderings of the endpoint functions have exactly the same analytic terms, exactly the same contact terms, up to some trivial prefactors, this minus I to n minus 1 here, that just come from the definition of the correlators. So that
I have a question.
this. Sorry, yes.
So this correlator in the second equation, this correlator between O1 and O2, I mean, if you evaluate it by the path integral method, it automatically comes with a time-ordered thing, right? So I don't understand this difference between the time-ordered correlator and just O1, O2. Because if you have O1, O2 if you evaluate it in the path integral automatically makes it time ordered, right? That's the standard
Good.
quantum field theory.
Good. Yes.
Intuition.
But O1, O2, this is, so the Whiteman function, these are operators. And if we don't think about the path integral, we just think about these as operators that act on states, then that gives Whiteman functions. All three of these can be obtained from the path integral, but on you have to use a funny contour. So the ordinary contour in the Lorentzian path integral, as you say, gives a time-ordered correlator. There's a Schwinger-Keldysh contour that gives the retarded correlator. And there's a contour with multiple back and forths in time that gives the Whiteman functions. And you can also understand these contact terms and understand the existence of these contact terms by thinking about those path integrals. So the contact terms come from coincident points on the contour in the path integral. And if you look at the contour, say for the Whiteman function, you find that actually when you account for the contour, you never have 2 points touching in that path integral. Even though it looks like they're touching in Minkowski's signature, they're on different parts of the time-fold contour, so you don't get contact terms. Okay, thank you. And that also I was going to mention, because the question of how are these terms really defined? Well, the same as in Euclidean, they come from the path integral. You can get them from the path integral by the usual ward identity type methods. You just have to use the path integral that's appropriate to your operator ordering that can go back and forth in time. Okay. So those are just some general facts about contact terms and this retarded correlator. Now we're going to talk about the null energy specifically and how to get it from the conformal anomaly. So this is now a CFT calculation. We're going to start with a CFT calculation and then go to QFT. At a conformal fixed point, the trace vanishes. Inside a correlation function, that doesn't necessarily mean you get 0. It just means that you get 0 at separated points. So any correlation function involving a trace is a pure contact term. And we're interested in this object, which is the retarded correlator of the ANEC in 2 traces. So it's going to be pure contact terms. We will now calculate this contact term using the conformal anomaly. In a 4D CFT, the trace is given by this formula here. So the first 2 terms are probably the most familiar. The first 2 terms in this, so this is the trace in a curved background. The first 2 terms are the conformal anomaly. So there's 2 anomaly coefficients in 4 dimensions. There's A and there's C. So these are the conformal anomaly, but there are also some other terms in the trace, which are these B terms. The other terms in the trace can be removed by counter terms, so that's why we don't usually talk about them. These are non-universal in the sense that they're not data of the CFT, because you can remove them by local counter terms. But we have to include them in this argument because we're going to be studying RG flows. And if you set these, you can set these to 0 in the UV by counter terms, but then they're going to be generated along the RG flow. So you're not allowed to set them to 0 in this argument. We have to make sure that they're included. Okay, so now we have the 1-point function. We can vary this with respect to the background metric to find all the contact terms in the trace correlation functions. The trace itself is the first variation of log z. The trace is a second variation, so we can get it from varying the first variation, etc. And we can extract from this trace relation all of the correlation functions involving the trace and any other number of stress tensors. There's a straightforward calculation now of the 3-point function, and accounting for all these analytic continuations, Wick rotations, ordering, etc., carefully accounting for all that, you find the retarded correlator of the average null energy with 2 traces. So here's the formula. This is a CFT formula that gives us the contact term in the null energy trace. And I've written it in momentum space So we get these terms that are analytic in momenta. A couple comments. First of all, it depends. There's a contribution here from the A anomaly. So here's A. The C anomaly dropped out, but these counter terms are still here. B1 and B2 are still here. But fortunately, they have different momentum dependence compared to the A term. So the A term is the only term with this K1 plus K2 squared momentum dependence, and the other terms have some other momentum dependence. That means that we can uniquely, so given the right-hand side of this formula, we can uniquely extract the A anomaly. The way to do that is by acting with momentum derivatives and then setting the momenta to 0. So we're going to act with this combination of momentum derivatives, which is designed to pick off this term in the correlation function, and therefore to pick off the A anomaly. And that gives us a formula in the box here, which is a formula for the A anomaly in a CFT. So we've now written the CFT A anomaly as some integral of some kernel times the retarded correlator. I've just taken the left-hand side and written it and done these momentum derivatives and written it in position space.
Is it easy to understand why the C anomaly dropped out?
Well, in formulas, it's easy to understand. I could point to why the Weil squared dropped out, but I don't have any kind of intuitive explanation for it.
I see.
So good. So this was our main result in CFT. This is in this formula, the entire integral comes from a contact term, right? Because this correlation function is pure contact term, and what this integral is doing is just extracting that delta function. Now we're going to take this CFT result and proceed to consider RG flows. So that brings us to the last part of the calculation, where we're going to study RG flows and get the A-theorem. So now we go to a QFT.
Sorry, just one quick question. So
Yes.
does this way of thinking about the A anomaly give you any insight on why this is a count of degrees of freedom?
No, unfortunately not. Well, not in CFT. In CFT, it does not. Maybe there's some way it does in RG flow, because the light rate this ANEC integral, it is a very natural measure. It is a natural measurement. Like particle physicists talk about it. So you could assign some operational meaning to it. But as far as the contact term, no, it's very formal. I don't really have intuition for assigning some physical interpretation to the contact term.
Okay, thank you.
So we'll consider now a QFT in 4 dimensions that flows between 2 conformal fixed points. In the UV, we have a CFT. That UV means the momentum invariants are much bigger than some mass scale, m squared, that is the mass scale of the RG flow, or the mass scale of the quantum field theory. Then in the IR, where these invariants are much below the mass scale, there's another CFT, CFT IR. The correlation functions of the QFT have to agree with the CFT at the fixed points. So in particular, the traces have to agree. We're going to tune those. So here I've written the trace in the UV. We're going to tune the counter terms, choose the counter terms in the QFT to cancel those extra terms in the trace in the UV. But now we've picked our counter terms. We're done picking counter terms. And that means that when we go to the IR, these extra terms will be generated along the flow. And since in the IR theory, the mass is the UV cutoff. So in the IR theory, this mass shows up in the place where the UV cutoff can generally show up in those trace terms. So this is why we had to include these trace terms in the whole discussion of the CFT.
I have a question.
Counter terms. Yeah.
So when you're canceling these counter terms, I mean, when you're canceling the extra terms using counter terms, doesn't that mean that these counter terms enter the action?
Yes.
So if they enter the action, then all the expectation values would then change, right? Because if you are doing the expectation values with respect to the previous action, the original action, and then you introduce counter terms, the action will change. And so then the expectation values are also supposed to change, aren't they?
Well, that's just part of the procedure of renormalizing the theory. And when we talk about correlators in conformal field theory, we're always talking about renormalized correlators. So, I mean, it depends what you mean by changed. I would say that just when we talk about the conformal field theory, we're really talking about this renormalized thing where you've already added all those terms. And that's what we usually do in CFT. So usually in CFT, these are the only terms that people even write because they're implicitly already renormalizing. So that's just the usual thing.
So in what sense do they enter then the IR action?
Well, the counter terms do not enter the IR action. The counter terms have been, so there was like a B1 tilde here. If we could have a B1 tilde in the UV, and the counter term removes the B1 tilde. But then in the IR, there are some terms that in the QFT, these are not these things. The point is that these things in the IR, these are not counter terms in the QFT. These are separated. These are separated points, true physical terms in the QFT. But from the point of view of the infrared CFT, they're counter terms.
Okay.
So they're non-universal from the point of view of the infrared CFT. But they are totally well-defined physical quantities in the QFT, and so they come with these masses in them. And these B's are, for a given QFT, these B's are well-defined numbers. Okay, so this is our G flow, and now the strategy is to apply our CFT formula to the infrared theory. Okay, we had a CFT formula for the A anomaly. We're going to apply the CFT formula to the infrared theory. The first line here is just the formula that we derived in CFT. So we said that there's some contact term in this correlator, and you integrate it in some way, and you extract the A coefficient. Now the important step is we can take that formula and replace the CFT correlation, the CFT 3-point function, by a QFT 3-point function. And the reason we're allowed to do that, so and it still gives the A anomaly in the infrared theory. The reason we're allowed to do that is because, remember how this worked, is that we were extracting the k-squared term in the correlation function. Well, and then setting k to 0. We were extracting the k-squared term and then setting all the momenta to 0. Well, that term you can calculate either in the CFT or in the QFT. They have to agree. That's what it means to flow to a conformal fixed point. So the QFT has to give the same answer here because it has the same leading k terms in its momentum space correlator. What we've done is non-trivial, though, because we've replaced a delta function, this contact term in the integrand, by something that's not a delta function. We've puffed out the delta function into separated contributions in the QFT. Okay, so now we proceed. The integrand on the second line has a UV contact term, so that we've taken that delta function and sort of puffed it out into separated points. It still has its own delta function inside it, which is a UV contact term. And then there are contributions from separated points. So basically what we're saying here is that the infrared delta function is a sum of two terms, a UV delta function and some separated points stuff. Now we move the contact term, the UV contact term, to the other side of the equation, expand out these nested commutators in the retarded correlator into Whiteman functions, and the result is the formula in the box. This is our main result, It's the sum rule that relates AUV, that minus AR, so this is the change in the A anomaly along the flow, to some integrated correlator. It's important that on the right-hand side is a QFT correlation function that only has contributions from separated points. We have moved all of the contact terms to the left.
And sorry, and so you moved all the contact terms to the left, and you used this fact, presumably, that the ANEC operator, I don't know, or EU acting on the vacuum annihilates it in the QFT, I suppose. And
Correct.
You've been able to drop the retarded symbol and just keep an ordinary correlator.
Correct.
Just to understand it.
That's right, yeah.
Okay.
So this is a Whiteman function showing up now.
Yeah, okay, right.
There's an important subtlety that somebody asked me about earlier, which is the semi-local terms. These are the terms with some of the points coincident and some of them separated. So there are actually operator-valued contact terms in the OPE of the stress tensor with other local operators, like the trace. That is, when you look at this OPE, there are delta functions times operators, non-trivial operators. And when you plug this into a 3-point function, you get these semi-local terms where you have 2 points coincident and 1 point separated. Those would ruin the argument that I just gave, because it was important that we could split up the correlation function into the UV and the separated. Whereas these semi-local terms are sort of partly controlled by the UV and partly controlled by the RG flow, and they would spoil they would spoil things. But they miraculously drop out of the formula, the sum rule formula that I just derived. I'm not going to go into the details of how this works, but you can consider all the possible semi-local terms, and they all drop out using the fact that we have a null energy here. So this kills a lot of things because there's no GUU component of the metric. And the fact that the null energy annihilates the vacuum, that kills a lot more terms. And we use the unitarity bound to constrain what sort of terms can appear. And in the end, all of these terms drop out of the sum rule. So that was something of a miracle, but it was essential for this whole thing to work. Here's a simple example, just to show that we can apply this formula in practice. So this is the example that I mentioned earlier of a free massive scalar field. This theory flows from a massless scalar field in the UV, with the anomaly given here, to a trivial theory in the infrared with anomaly 0. The stress tensor in this theory is just quadratic in the field, and you can calculate its correlation functions by Wick contractions. So the Wick contractions for the stress tensor trace give you this triangle type loop diagram. So this is a stress tensor that's giving phi in its Wick contractions. So when you calculate this 3-point function, even though it's a free theory, the 3-point function momentum space is a loop diagram. And you use this loop diagram to calculate the 3-point function, plug it into the sum rule, and check it. You can check explicitly that it gives exactly the expected change in the A anomaly. So this is how these sum rules work in practice. Now for positivity. Okay, so we have not yet gotten the A-theorem. We got the sum rule, but we have not yet gotten the A-theorem. So let's look at this sum rule again. It's not obvious that this is positive, because it is written in terms of the average null energy, but it's not written in terms of an expectation value of the average null energy. We want to apply the average null energy condition, which says that the expectation values of the average null energy are non-negative. So we need to somehow rewrite this formula as an expectation value in some state. The sum rule in the box here suggests using a wave packet with a kernel that looks like the terms in here. So we're going to insert, so we're going to make a state, which is a trace acting on vacuum with some kernel that depends on the transverse direction. We just choose a transverse direction and put that inside the integral. And then we insert it with some non-zero momentum omega in the null direction. Finally, we restrict the integral to half of Minkowski space v less than 0, just because the sum rule here has a v less than 0 in it because it came from retarded correlator. If you're used to the Hartman-Maldacena conformal collider bounds and familiar with that, then it's helpful to compare these two things. So in the Hartman-Maldacena setup, they insert a wave packet. These pictures are Minkowski space. And so they insert a wave packet near the origin of Minkowski space with some energy. And then the detector, or the average null energy operator, is inserted, in their case, very far away. So it's inserted on Scri plus at some direction on Scri plus. That's the blue line here. Is there a question?
I have a question. Yeah, can you go back to the previous slide? So this e to the minus u square by sigma square, is it a smearing term?
Yeah, that's just to make the wave packet a finite size. So sigma is just chosen in order to, there's some, yeah, sigma is just an IR regulator.
I see.
So the IR regulator is setting the size of these wave packets that I'm talking about here. So the wave packet in Hartman-Maldacena is inserted near the origin, and then they put the ANEC at infinity at Scri plus. In our case, it's important that our wave packet actually hits the detector. Okay, so we're putting the detector through the origin. We can put it at Scri plus, it's just a coordinate change. But the important thing in this picture is that we're not putting the wave packet far away. The integral actually hits the detector, or comes up very close to it. And that's important because we're using this to basically to build a contact term by taking separated contribution and then going to the IR. Now that we have the ansatz for the wave packet, we can go through a similar kind of calculation that I use to derive the sum rule to calculate this average null energy at low frequency.
Sorry, Tom. So this wave packet, this psi n state is half the wave packet?
Yeah, it's half a wave packet because it's only inserted, if I go back, that's this restriction to v less than 0. Yeah.
I see. And is it clear that it's not quite, it's kind of diagonal, right? The reflection is happening in the diagonal. So is it still a norm? Because that would suggest that your Hilbert space is defined on the light-like slice.
No, the reflection is still in Euclidean time. Because we insert the wave packet twice, right? We insert the wave packet once, and then there's a null energy, and then there's another insertion of the wave packet. These two traces are each a wave packet that's inserted in exactly the same place, but on either side of either side. So it's the ordinary, it's like the ordinary Hermitian conjugation where you flip the Euclidean time.
Yeah, so that is not clear. What I mean, so the discussion so far has been in the Lorentzian space, right? Because I would imagine that is important to define even the operator E of U.
That's right. It's all in Lorentzian.
So now even the definition of the state in the last line is done in Lorentzian space, or not really?
Yeah, this is in Lorentzian. Yeah.
Yeah.
Sorry,
so
I thought you were
by Euclidean reflection.
I just meant in I epsilons. So this is the state. You're right. It's inserted in Lorentzian.
Okay.
But this operator ordering here has some I epsilon prescription, and it's just the ordinary one where
I see.
Yeah.
I see. Okay. I think I understand.
So now we calculate the average null energy in this wave packet state, psi of n. And the leading term at low frequencies is delta A, AUV minus AIR times some factors like the IR cutoff and the frequency. But the important thing is that now this is the ANEC. This is actual expectation value of the null energy. Therefore, the ANEC implies the A-theorem, AUV is greater than or equal to AIR. So this is now the derivation of the A-theorem. This was conjectured by Carty a long time ago, and as I described earlier, first derived by Komargatsi and Schwimmer using the Dilaton S matrix.
Sorry, Tom, just to make sure I don't lose the thread, you had that relation between AUV minus AIR and something integrated in the QFT. And now you evaluated that integral in the QFT on this wave packet state. Is that right?
Correct.
Okay. So, I mean, of course, since it came out to, I mean, the fact that it came out to be positive is probably a very robust statement, right? Just from the fact that that right-hand side was the inner product of, or was the expectation value. Can you just argue that it's the expectation value of a positive operator, or that's too quick to do? That EU is a, you know, it's an, I mean, do we, that is to say, so you had AUV minus AIR equal to something on the right-hand side, which was then expected. Could I think of that right-hand side as the expectation value of EU?
You mean in the sum rule?
Yeah, in the
like
sum rule.
Back in this formula.
Yeah.
Yeah, you.
Oh, no. Yeah.
You can.
Yeah, exactly.
You can. It's just that when you the reason we had to go through this extra couple slides, this extra step, is basically the IR regulator. So if you really try to think of this formula already as an expectation value, it's tricky, and you have to be careful about the IR regulator in order to define the state. But yes, you can think of it that way, that when you have a positive kernel that's translation invariant, you have to be a little more careful about what you mean by positive kernel. And that's just what I've done by introducing this wave packet.
I see. Okay, thank you.
Okay, I had some comments about Lorentzian inversion.
The dot product could take any sign, right? So I wonder how that becomes positive.
It's only after doing the integral. The dot, yes. The integrand is certainly not positive, but when we do the integral, it's now an expectation value in a state.
But what happened to the dot product when you did the integral?
What do you mean by what happened to it?
Meaning, sorry, can you just flash this form of the psi n? Yeah, so here, yeah, when you
well, it shows up twice, right? That dot product shows up twice, so
okay,
one for each psi n.
No, I mean in the x1 x2 piece, that in the blue square, in the blue box.
Yeah, but this thing is not isotropic. So this thing depends on the directions in some complicated way. And then that has to combine with this to give something positive.
Okay. All right.
But in general, do you expect that n cap dot x1 vector times n cap dot x2 vector to be just x1 dot x2? Do you expect that?
No, that's not true in general. But just think of this. So this term here in the transverse direction is just x squared plus y squared.
Yeah.
Okay, so what I've done here is this is like x, for example. So when we take the expectation value, we get x squared. But everything is isotropic or everything is rotationally invariant in the transverse direction. So x squared plus y squared or x squared is perfectly good. X squared is the same as x squared plus y squared.
No, but why is x1 dot x2 x squared plus y squared? It's x1 x2 plus y1 y2. No?
Right. Right.
Right. That's what. Sorry. Yeah, that's what I meant by x. So this is x1, x2 plus y1, y2. But if we just replace this by x1, x2, the transverse x1, x2, then we would get exactly the same formula up to a factor of 2.
I see. So this is this when you say this expectation value, you are summing over these n orthogonal or something like that.
Well, that'll just give a factor of 2. We can either sum over them
Okay.
or not.
Okay, fine.
Yeah. Okay, I had some comments about Lorentzian inversion, but I'm out of time, so maybe I think I'll just go over this 2 slides and jump to the conclusion. You can ask me about it if you want. So light ray operators are an interesting new handle that we have on studying the RG. There are additional interesting things that happen in 2 dimensions that I did not have time to talk about, but we wrote a separate paper about the situation in 2 dimensions. The basic reason that you have new things you can say there is because the average null energy operator under some assumptions is equal to the null momentum generator. That allows us to calculate things like ANEC to the n inside a correlation function and to get new constraints along the flow from that. We can reproduce Zamolodchikov's result, but we can also get additional new constraints on the C function along the flow. And we end up finding some nice short statement, which is that the C function is a completely monotonic function. It has which means it has alternating derivatives as a function of m squared. 6 dimensions. So I motivated some of this by talking about higher dimensions, and we don't understand it. Unfortunately, our method does not seem to work, at least not so far in 6 dimensions. It's straightforward to derive a sum rule like I've done here, but positivity is hard, and we have not managed to show that the sum rule is positive. And I'll just conclude with the statement I made at the beginning that there's still a lot to be understood about these c-theorems. Okay, thank you.
To show positivity, you came up with these nice wave packets in the previous slides. Is it correct?
Yeah, the wave packet, that's how we showed positivity. That's right.
Yeah, so for 6 dimension, what was the bottleneck which didn't let you compute this, didn't let you get the positivity? Was it just you couldn't come up with a better wave packet?
The problem is that the natural thing to study in 6 dimensions is a higher point function. So actually the way to the A anomaly in 6 dimensions is still believed to be A. It's still believed to be an A-theorem, but the A anomaly shows up in the not until higher points. So in 6 dimensions, we study the ANEC trace 5-point function as opposed to the 3-point function. And then in that 5-point function, we've been unable to find a nice way of understanding it as an expectation value.
Is it these kernel things, these x1 dot x2 things, they appear in a way that they're not quite squares?
No, the issue is that you get terms like trace, ANEC, trace in that ordering, and those terms get in the way.
I have a simple question, like when you have these 3-point functions of stress energy tensors, aren't they related to dilaton, graviton 3-point functions in the ADS space, corresponding ADS space? Can't they computed more easily there?
Well, I don't know about more easily, but yes, they should have a dual calculation, but it's a calculation in an RG flow. It's not a calculation in ADS. It's a ADS with an RG flow turned on.
Yeah, that is correct. Yeah, so that would be something. Yeah.
So Tom, what happens?
Sorry,
Sorry,
just one sec, Abhijit. Just one sec, if you don't mind. Just as a follow-up, I had a similar thought, which is, as you correctly say, we have to look at a RG flow. But if we look at an RG flow in the context of ADS-CFT, then is there some kind of geometrical way to understand some of these results in the bulk?
Maybe I don't have an answer to that. I think so. There should be. There's a very interesting series of papers by Myers and Sinha and others later about RG flows in the bulk and the c-theorem in the bulk. And something I find really intriguing is that in holographic theories, the c-theorem is simple and universal. In fact, the c-theorem of Myers and Sinha comes from the bulk null energy condition.
Yeah, that's what I was thinking. Yeah, I mean, the ones I've studied, I'm not sure it's Myers and Sinha, but usually it's the Raychaudhuri equation used in a flow, if I recall properly. Some variant of that, during the flow, which gives a kind of c-theorem, where
That's
the
right.
interpolated geometry is a domain wall of sorts, right?
That's right.
Yes, it sounds like there should be some way for those cases to relate your results.
Yeah, we would like to understand. So the dream, and I don't know whether this will work, but a dream is to sort of understand how our sum rule is related to that, and then perhaps we could even use it to go to other dimensions because that result is independent of dimensions.
Yes. Okay, beautiful. I see. Okay, thank you. Please go ahead, Abhijit.
Thanks, Sandeep. So in this 4D case, what happened to the other orderings of theta e? Those somehow didn't appear on the Whiteman side.
Yeah, because E annihilates the vacuum. So if it doesn't show up in the middle, it drops out.
I see.
I have another question. Like in your paper, you have said that in order to get from the retarded correlator to the expectation value, you have to put some z equals I, where I is the root of -1. So could you explain how that comes about?
Well, I think you're talking about a different thing in our paper, which I do have a bonus slide about. But this is a different argument. It's not a sum rule. It's just when you calculate, if you have some correlation function like this, which is like t momentum t, then this p sub z bar is an ANEC operator essentially. Well, this is only positive if it's an expectation value. And the way to turn this into an expectation value is to choose, well, first let's remove the p, ignore the p. Then for this to be positive, you just need the insertion points to be reflection symmetric. So choosing z equals I or minus I here is just, sorry, this should say I, not minus I, but this is just choosing it so that you can interpret these as states. We need to be able to translate the correlation function into some state created somewhere, and then you evaluate the expectation value in that state. So that's the purpose of inserting these things in the complex plane.
I see. Okay.
Sorry. Hi, Tom. I have a sort of question. So usually I think of the ANEC as coming from an information theory point of view. I think of that as coming from the monotonicity of relative entropy under shape deformations. But one might have thought of the c-theorems as some kind of monotonicity under RG flows. And well, do you have any comments on why these seemingly different things are related?
Monotonicity, you mean when you say, sorry, you think of the c-theorems as monotonicity, you mean of relative entropy?
Under, say, RG flow. Roughly.
Yeah. I don't know. There are now these. So there was this paper in the spring that showed that that unified all the c-theorems in 2, 3, and 4 dimensions with various defects, et cetera, that sort of unified them all in terms of strong subadditivity. That could also be stated in terms of relative entropy. But it seems that, so if you take the sum rule that I just gave, you can restate that as a application of monotonicity of relative entropy, just using your paper. But it seems to be a different application of relative entropy compared to any of the previous ones. So I don't really have I don't have a good answer. It just keeps showing up in different ways.
Okay, thank you.
Hi, Tom. Can you explain once more this additional constraints that you get in 2 dimensions? How do you get them?
Sure. Yes, this is what this extra slide was for. So there's a very easy proof of this c-theorem, just Zamolodchikov's c-theorem, using the ANEC. And here it's the entire thing is on this slide, basically. So in 2 dimensions, you define the stress tensor 2-point function. There's some prefactor by dimensional analysis, and then there's a form factor that depends on the scale. This is in QFT. So we're looking at the stress tensor 2-point function QFT. Now, in Zamolodchikov's argument, he uses this one together with the other components of the stress tensor, conservation, etc., and combines them in some clever way. But there's an alternative thing you can do, which is what's done on this slide. The idea is just to take this correlator and plug in the null momentum generator in this correlator. So when you plug in a null momentum generator in this correlator, that gives you a d by dz bar, which you can rewrite as a d by dm squared. And then now you have some inequality on scale derivatives of that form factor.
I see.
Inserting n of these, what you find is this relation here that says that the form factor has alternating signs in its derivatives under m squared. And so that's one of the, we get various constraints of this type, but this is the simplest one, that this prefactor in TT has alternating derivatives in scale. So that's these generalized constraints.
I see.
And what
it turns out these completely it turns out these completely monotonic functions are mathematically interesting, and mathematicians talk about them. You can characterize them as functions with a positive inverse Laplace transform. And that can be understood in terms of the spectral representation of the correlator as well.
And what is the problem in doing it in 4 dimensions? Complete monotonicity demonstration.
Just the form of these correlators. They're not so simple. You can actually derive completely monotonic functions in 4 dimensions, but they're not the same function that shows up in, or at least they don't seem to be the same function that shows up in the c-theorem. Anytime you find some function like this, though, you can get something to be completely monotonic.
Yeah, but I would guess that if you can show something is completely monotonic, wouldn't it be? Wouldn't it be easier to show the c-theorem using those? Because if they're completely monotonic, then integrating them would just simply say that CUV should be greater than CIR, right?
No, it doesn't. It doesn't end up quite so simple, because what you end up with is some. For example, you could end up finding that the function like divided by z to the 6th or something is completely monotonic, and then the function itself could vanish at the endpoints, but and not really tell you anything about the CFTs, but still have some interesting behavior along the flow, and that's the sort of thing that happens.
Okay.
Okay. If there are no further questions, let's thank Tom again for a wonderful talk. Thanks, Tom.
Great talk, Tom.
Thank you.
Thanks a lot, Tom. That was a great talk.
Bye.
Okay. Good to see you all. Bye.